So in the usual place, or week 12 materials, you should find an Excel workbook called W12D1. We're going to walk through these three examples today, but I want to start by demonstrating our t.test command and review some of our visualizations and pivot table techniques just using this first example here. So we're interested in whether the mean weight of Labrador retrievers is less than or equal to the mean weight for Basset hounds. To answer this question, we collect two simple random samples, one for labs, which is in column A here, and one for Basset hounds, which is in column B. The data is to the left. So the first thing we want to do is create a visual to inspect for differences between the samples. All right, so I'm highlighting here, these are differences between the samples we collected, not necessarily differences in the population. That's why we need the hypothesis test. We're going to summarize their means and standard deviations using a pivot table. And then lastly, we're going to use a significance level of 4% to test this claim. So let's start with the visualization piece. All right. Now remember, our main visualization for this is going to be a comparative box plot. So what we want to do is highlight all of our data. This is a little bit of a review from Unit 1. Highlight all of the data, and separate variables will be in separate columns when we're doing a box plot. We'll go to Insert, and then we find the middle chart. If you hover over it, it should say Statistical, and we want to choose the box and whisker plot. So this will automatically create a nice comparative box and whisker plot. I'll make it big so we can kind of investigate this a little bit. All right. Keep in mind that the box plot farther to the left comes from the data that's farther to the left. So in blue, we have our labs. In orange, we have our Basset hounds. And we can see that it looks like the labs, the weights for the labs are actually shifted up a little bit more from the Basset hounds. But again, this is based on a random sample from each population. So we can't necessarily just say, oh, since it happened with these samples, that's what's actually happening in the population. We still need a hypothesis test. But this is at least a little bit of visual evidence that perhaps that null hypothesis that Labradors weigh less than Basset hounds is false. In our next component, I want to use a pivot table to kind of get some summary information about these two different data sets. Now our data is in sort of a strange format. It's in what we call wide format, which we're going to contrast against long format when we look at the second example. This wide format where you have each column here ends up being a weight measurement for the two different populations. This is how the t.test command and our visualization command tends to work. So this is actually going to be preferred when we're going to do our analysis in Excel for hypothesis testing. However, the pivot tables work a little strangely, so I just want to give you a sense of how to do this. So the first thing we're going to do, just like we've done from Unit 1, is highlight all the data, do an insert pivot table, leave this as it is, and let's put this pivot table in the existing worksheet. So we're going to toggle this existing worksheet, and we're just going to grab the cell below our pivot table prompt and hit OK. Now, normally what we do is we would think about the variable of dog breed, and we would have a list of whether the measurement is associated to a Labrador or a Basset hound. Now, in this case, we're in this wide format, so it's a little bit different. So the way that we can work with this, right, is we can drag Basset hounds to values and Labradors to values. And what I'm going to do, just so that this fits properly, is I'm going to take this values thing that appears in the columns, and I'm going to send it to rows. And what you can see is it starts saying, well, all the measurements under the Basset's column, here they've summed them, and all the measurements under the Labrador's column have been summed. So I don't want a sum, maybe I want an average. So what I can do is click on the I, or the little arrow if you're on a PC, and change the summary type to an average. So I can change both of these, and now I look at the mean weights, right, the average weights for Bassets versus Labradors. I can also rearrange these, so if I kind of drag my Labradors above the Bassets, I'll end up with the Labradors going first. And we can see this in our visualization chart. We've got a 67.9, about a 68 for the mean, and you can see that this X is the mean for the Labrador measurements. And lower than that, at what looks to be about maybe a 65, is our measurement for the Basset Hounds. It looks 64-ish. We can add to this table just by dragging another copy of both measurements into the values and then changing the way that we summarize. So for example, maybe I wanted the mean and the standard deviation. So I can select and replace that sum of Labrador measurements with a standard deviation of Labrador measurements and do the same thing for my Basset Hounds. And now I've got up in the first two entries, the average and the mean and the standard deviation of my Labrador weights and the mean and standard deviation of my Basset Hound weights. Now what I want you to do next, just to make sure that you're kind of understanding this technique, using a pivot table on a wide format data, right? Common measurement of weight, but we've broken up whether it's a Labrador or Basset Hound by our columns. What I want you to do is I want you to add a sample size count for each one of these measurements, one for the labs, one for the Basset Hounds. So hit pause, give yourself a little bit of time to think this through and see if you can add a sample size count for each one of these. Okay, good. So what we would do is drag an extra copy of the Labrador measurements and the Basset Hound measurements into our values. And then we want to change the way that we're summarizing these. And to get a sample size count, we're just going to do count. So we have 25 Labrador measurements and we have 19 Basset Hound measurements. Okay? Now, each one of these, and maybe if you want to, you can kind of highlight these in the appropriate colors. We'll do Labradors in blue, and we'll do Basset Hounds in orange, just as it's, so it kind of matches up with our box plot up above. All right, so we're comparing Labrador and Basset Hound weights. Okay. Now our last part is we want to use a significance level of 4% to test the claim above. And remember, our claim here is that the mean weight of Labrador retrievers is less than or equal to the mean weight for Basset Hounds. So let's write out our null hypothesis. Let's say mu for labs is less than or equal to mu for Basset Hounds, okay? And so long as this is clear, which mean you're talking about, you could also do something like this. You could say labs corresponds to 1, Basset Hounds corresponds to 2, right? And you could do mu1 is less than or equal to mu2. It doesn't really matter how you set this up. I just want to make sure that you're clear in what your null and alternative hypotheses are. Our alternative hypothesis here is that the mean for labs, the population mean for labs, is greater than the population mean for Basset Hounds. And this is what we suspect is true just based on the box plots and based on the actual sample data. But now we're using the power of a hypothesis test to kind of lift this to a test on the population level. So we can see that it's true on the two samples we collected, but is it true on the population level? That's what we're trying to determine. We do need to know the type of test. In this case, our H1 is pointing to the right, so this would be a right-tailed test. But more specifically, it's a one-tailed test. Meaning when we draw, when we kind of draw that p-value region, it's only one tail. It's not two-tailed. Okay, and this is important because when we go to use our t-test command to compute this p-value, we have this tails component that we're going to set either equal to 1 or equal to 2, depending on what our null hypothesis is, depending on the type of test. In this case, here's our null hypothesis for this Basset Hound example. We know that it's a right-tailed or one-tailed test, so we're going to set tails equal to 1. And keep in mind, type is going to equal 2. So our approach here is to compute the p-value with a t.test command. Okay? T.test prompts us for 4 different pieces of information. Array 1 is just going to be the data for our Labradors. So we're going to highlight A2 to A26 to pass in the sample data for our first population. This array 2 is going to be the data range for our second population, which are the Basset Hounds. So we're going to pass in B2 to B20. Now keep in mind, these won't necessarily be the same length. In fact, we saw we have 25 observations for the Labs and 19 for the Basset Hounds. Labs are more common. All right. Again, based on the type of test, this is one-tailed. Our tails argument is going to equal 1, according to our slides. In type, we always said equal to 2. Okay? Now what this does is it takes our two pieces of data, it computes sample means, sample standard deviations, the two individual counts, and it converts all of this information to a single t-distribution and then computes the p-value based on the type of test, one-tailed, based on the type of test, computes that p-value automatically for us using the appropriate probability model. So it does a lot of the work we did with one sample test in the background, and it spits back just the p-value for us to make our conclusion. So when we hit enter here, we're going to get the p-value for this test. And we can see that it's about 3%. Right? And remember what we do with this p-value. Right? Once we have the p-value, we compare it against our significance level, alpha. Specifically, if p is less than alpha, reject H0, reject that null hypothesis. If p happens to be greater than or equal to alpha, we fail to reject. Okay, so this is a quick summary. In my opinion, as you're studying these things, it's a good idea to kind of write these out every time you come to a conclusion. And after about a week of doing that, it becomes second nature. You don't really even have to think about it as something that you would study. All right, so in our case, our significance level was set for 4%. So we have a significance level or an alpha value of 4%. Let's make this blue, I guess. So 0.04 is our comparison. And we can see that we're in fact less than this significance level. All right. Oops, not enough space. So we're less than the 0.04. So summary, we should reject our null hypothesis claim. Now we get to write our conclusion. Now remember, the conclusion should be a little bit more well-developed, right? You should explain what's actually happening here. Our samples, right, because we actually collected two samples, one for Labradors, one for Basset Hounds. Our samples provide sufficient evidence to suggest that the mean weight for Labradors is greater, right? We're actually siding with our alternative hypothesis here, is greater than the mean weight for Basset Hounds at the population level. Okay, so this is no longer something that we've observed on a sample through either a visualization like a box plot or through actual sample statistics like we did with our pivot table. This is no longer a statement about our sample. This is now a statement about the population means for each one of these dog breeds. And according to our evidence, according to our sample, we conclude that Labradors have a greater mean weight in that population than Basset Hounds do. So Labradors, typically speaking, are going to weigh more than Basset Hounds. That's how we use this hypothesis test. So the t-test command is going to shortcut a lot of our work with this general process of hypothesis testing. Now you still need to know that process, of course, to do the one sample tests for this class. But with the two sample test, when we're comparing means between two populations, things are going to go a little bit quicker. Here's our new general process. Write out the hypotheses, the null and alternative hypotheses, and these will always be in terms of comparing a mu1 to a mu2. You're comparing the population mean of one population against another. And these can take three general forms, right? You could have a null hypothesis that the first population is greater than or equal. You could have the first population less than or equal to the mean for the second, or you could have exact equality. So we still have sort of three tests. The t-test command, however, simplifies this into one-tailed tests and two-tailed tests and kind of automatically makes the adjustments for you, so you don't have to worry about differences between the left and the right tail. So in this case, we write out our null and alternative hypotheses. The type of test, right tail, left tail, are considered one-tailed tests, means that you would plug in a 1 for the tails argument. And a two-tailed test, when you have exact equality as your null hypothesis, means you plug in a 2 for your tails argument. Okay? So once we know the type of test, we know what that argument should be in our t.test command. Then we're going to use the t-test command, t.test, to find the p-value for the hypothesis test that we've been setting up. So we don't find a test statistic anymore. We don't specifically use t.dist to find our p-values. We use t.test instead. And then we make our conclusion. Once we have that p-value that comes out of that command, we compare it against our significance level and decide to either reject H0 or we say that the samples didn't provide enough evidence to show that H0 was false. So here's our new general process. It's a little bit quicker because the t.test command does a good amount of work. All right, let's go back and consider a few more examples.